Hello everyone. So now welcome to this lecture, and let us quickly review what we have done in the last lecture, and that is we, as you can see on the screen, that we discuss about the generalized velocity, because we had already discussed what is the generalized coordinate, that we want to have unique independent coordinates, that those coordinate has to be independent, which can uniquely define the configuration of the system, that is your generalized coordinate. And then when we have a generalized coordinates, that is these are my qj, then what you do, you differentiate it, and then you get the generalized velocity, as we had already discussed in case of this when we move from physical space, that is my Cartesian space, that is from xy to r theta, then in that case my r dot and theta dot are going to be the generalized velocity. And if I constrain the system, that is r dot is not time dependent, it is r is constant, then the generalized velocity is just the theta dot in that case. And similarly, in a spherical polar coordinate, what you do is like our generalized coordinate as r, theta and phi, and the moment we constrain the system, that is r is constant, then this r dot respective to this r dot is going to be 0, and just the two coordinates which are theta and dot, the corresponding to that theta dot and phi dot is the generalized velocity. Okay, so with this, and then we move further and we discuss about the concept of the virtual displacement, that is the imaginary displacement when you do something at the instant of in any instant of time, basically, because when you talk about the real displacement, the time is involved. Okay, the body is really displaced from one position to another position when you apply certain force, and then the time is involved. But if the time is not there at any instant when you are applying the force, and the body is supposed to be imaginarily deformed or infinitesimally have the change in the configuration because of the change in the generalized coordinate, then that is the virtual displacement. That is, we don't take into consideration the time delta t is 0, and the concept of we discussed the concept of the virtual displacement is discussed to basically get rid of the work done by the constant forces, and that is the principle of our virtual work. We discussed this that delta theta in this case, if you remember, delta theta is my virtual displacement in case of which is the infinitesimal oscillation of the pendulum because of the tension force in the string. If you remember, this is the constant force. Similarly, we discussed in case of the bead, which is the constant force is going to be the normal force on this, and because of this the work done into this virtual displacement is going to be 0. So all in all, we discuss about and then we discuss that how we this, if you remember, this delta ri, because when you talk about the real displacement, the time is involved, delta r by delta t, but when time is 0, so then what you is get is this delta ri is the virtual displacement of the system, that is change in the configuration. It is a mathematical tool. We actually discuss it, and this mathematical tool is helpful in defining the principle of the virtual work. And what is the principle of the virtual work? That is, the work done by the constraint forces are always going to be 0, and we discuss certain uh, um, examples about that. And before that, we discuss what is the equilibrium case and what is static equilibrium, and we discuss then what is the dynamic equilibrium, and then we discuss the case of the water droplet. And then finally we discuss the virtual work, that if you do a virtual displacement because of some force, whatever the force it is, we are not discussing it here, and then the work done by that is going to be the virtual work for that case. Fine. And then uh, we move to actually what the principle of virtual work is, that if I have the work done by a forces, this delta ri, which is the virtual displacement, is going to be 0, but the force can consist of my applied force, this one, and as well as the constant force. Okay, so if I take the dot product of this with, because of this is delta Ri here, so I have two components, two work done by this work done by the applied forces, this one, and the work done by constant forces. So we now restrict ourselves to the system to which the virtual work done by the constant forces are going to be 0. So that is, we are demanding that it is going to be 0, and we discuss about this bead problem because of this work done by this normal force, which is the constant force, tension work done by this tension force, which is the constant force in case of the simple pendulum. And in a full detail, we actually calculated using the Newtonian mechanics, that by equating the different forces which is acting, this is gravitational force as well as the tensile force, equating the components of these two forces, we actually come to the differential equation of this one, differential equation of the simple harmonic motion, that is the motion of my simple pendulum. But if I apply the principle of virtual work, that the forces which are acting in as a constraint in case of the simple pendulum, which is the tension, so if I calculate the work done by the tension for the virtual displacement is 0, sorry, is 0. That is because of this delta R is my delta theta connected with delta theta, because delta x, if you remember, this is my L cos theta, and delta y is L sin theta. So we calculated T dot dr, that is the work done by this tension force that is in virtual displacement is 0. So we discussed that when it is 0, then the other force, which is my mg, is the only force, and because the gravitational force is a conservative force, we can apply the conservation of energy, and then on the basis of that we calculated the same differential equation. So there is two things that we calculate these with considering all the forces component, equating through the Newtonian dynamics, we get the same differential equation, and by applying the virtual displacement work, which is going to be 0 because of the constant forces, we get the same conclusion. So this is why we define the virtual displacement and the principle of virtual work, that because it is the calculation not for this simple pendulum, but we do have a complicated system where the different constants are there, and we can use the principle of the virtual work actually to work out to ease the mathematical calculations. So moving further, for the system of equilibrium, that means we talking about actually the static equilibrium, and the work done, that is Fi dot Ri, for all forces and constant forces which are acting on the system is 0. Then the principle of work state that Fi, the work done by this Fi, the applied forces for this delta Ri, this is virtual displacement, is going to be 0. So this means that the virtual, that means delta t equal to 0, work for the applied forces is going to be 0. This is the statement of the principle of virtual. If you remember that we started from this from here, that if I, the total forces which is acting on the system, delta Fi di, and this force Fi is my applied force, this and this constant force. Okay, so we demand that the constant force, because of the constant force, the work done is going to be 0, and that this, we demanded that this is going to be 0, and we actually prove it with certain example, and we see that by demanding that, my calculation is going to be easy. So when the one part is going to be 0, then the second part, this the work done by the applied force is going to be 0. This is the principle of the virtual work. So we cannot in general, but you see that here we have this is my delta Ri, because mm, Fi is the coefficient, so we cannot in general set the coefficient of delta Ri is 0, because the coefficient of delta Ri here is my applied forces, because delta Ri are not independent. You see that if I have a kind of thing that say sum over I, if I have alpha I Fi, so I can have, say, I go 1 to 3. So if I have alpha 1 F1 plus alpha 2 F2 plus say alpha 3 F3 if I explain it like so, but this is going to be 0. But if these alphas are not independent, that's alpha 1, alpha 2, alpha 3 are not independent, like there's some constant, this alpha 1 is like say alpha 1 plus alpha 2 is equal to 2 alpha 3. These are they are not dependent, they are not independent, they are dependent. So in such cases, if I put alpha 1 plus alpha 2 is equal to alpha 3, so what I can get is this alpha 1 f1 plus alpha 2 f3 f2 plus alpha 3 is going to be alpha 1 plus alpha 2 divided by 2 and f3 and so on. So this alpha, or if I say this is alpha 1 and this f1 plus 1 by 2 f3 plus so on. So now you see that f1 and f3 are, I cannot put the coefficient of alpha to be 0 because alpha 1, alpha 2, alpha 3 are all dependent, so that I cannot put individually the force which are being applied to equal to 0. So that's why we have written that we cannot in general set coefficient of delta Ri is 0, because since the delta Ri are not independent, it is generalized coordinates qi which are independent of each other. Because if you say that if we're working in physical space, that is my x square plus y square equal to L square in case of the simple pendulum. So x and y are not independent, they are dependent, but the generalized coordinate theta is, if you remember, is independent coordinate. So for this case we cannot put the equation coefficient of delta I going to be 0. And let me remind you, the principle of virtual work said that the work of the applied forces is 0, okay, for this virtual displacement. What is the usefulness of this? So basically the purpose of defining the principle of virtual work is that it gives you a tool to test the equilibrium, because we're talking about the static equilibrium. Principle of virtual work is for a static equilibrium system. So when we are considering demanding the system is in a static equilibrium, so that particular relation gives me to test the equilibrium without directly considering the unknown constant forces, because we already demanded that the work done by those forces are going to be 0. So it is going to be extremely powerful mathematical tool to solve the complex mechanical system which are going through a certain constant. So let us do the mathematical form with generalized coordinate. So if I can define this you know that I define the generalized coordinate is Ri. These are my q1, q2, q3, qn are my generalized coordinate which are transformable from configuration space to the physical space. And this virtual displacement is if you see, is defined as delta Ri, because R depends upon Q. So my Ri is depending upon Q, J as well as T. So that's why this is I can write this delta Ri. So delta Ri is delta Ri, because depends upon Q. So I differentiate partially differentiate with respect to Q, and then this delta Qj. And because it depends upon T also, but we are defining the virtual displacement, so it is independent of the time. So the time component what is here is going to be 0. So whatever it is like is my virtual displacement. So we define the generalized coordinate, and then we define this virtual displacement. So the virtual work is del W is Fi dot Fi applied forces and this virtual displacement. If I put Fi here, and this the expression for delta Ri is delta Ri is my delta Ri upon delta Qj. If I use this here, so this is my delta Ri, and this quantity, this one F with this is known as the generalized force in this case, okay, Fi dot delta Ri upon delta Qj. So is the generalized force which is giving me the component of the generalized forces, the corresponding to coordinate Qj. So, but for equilibrium static, when we discuss about the static equilibrium, so that means the system, whatever the forces are acting on the system, overall is the forces are going to be zero, so that the system is not moving, the velocity is zero. So the work done is for equilibrium is going to be zero. So this denotes the work done by all the this one denotes the work done by all the generalized forces Qj in the arbitrary displacement of the generalized coordinate, that is delta Qj. So delta Qj is the arbitrary infinitesimal virtual displacement due to the generalized forces, whatever the generalized forces are acting on the system. So work done by that zero, so that my system is in a static equilibrium. So since now here in this case, this delta Qj are all independent, because there in that case we are dealing with delta Ri. So that in that case, that was my Fi, and that was delta Ri. So that delta Ri was my coordinates in my physical space, which were all dependent. That's why in that case we were not able to put this coefficient of this going to be zero individually. But now here we have the generalized coordinate. So because generalized coordinate are all independent coordinates, so these are this the displacement in that is also going to be virtual displacement is going to be independent. So with that conclusion, that with argument, that we can conclude that, see, because delta Qj's are all independent, then we can have this forces are going to be zero for all j, which is analytically based on the concept of that the demand of the virtual displacement or static equilibrium. So this is what we have for this principle of the virtual work, that all the generalized coordinates are going to be zero for whatever the forces are acting on the system. So one point you can note, that this is the Qj, because what to define is delta W. This this delta W here is delta W here is my Qj, and this delta Qj. Okay, this is what. So this Qj, whatever this is, Qj need not have the dimension of the length, because work done you define is F dot ds. Fd you define with that sine theta, cos theta is going to 0. So d, this role play by this Qj is need not have the dimension of the length, so that the Q do not, this capital Q, this is with the generalized force, do not have necessarily have the dimension of the force, but this total altogether total is going to have always have the dimension of the work. For example, Qj is not a force, Qj is a torque, and delta Qj is not the length, it is a differential angle. So nj dot delta j, this is going to be, if this is my torque and this is delta theta j, is a differential work. So this is one remark for this. Now if you go for move for some example based on this bead, that if this bead is moving down with this delta r, my virtual displacement, and the constant force is n, okay, and this the other force, which is mg, is acting on the system. So now if I apply the virtual work, this is the forces which are acting is mg, and because of this, the displacement dot dr, this is one work done, and this is the work done by this normal force n dot delta r. But because n is perpendicular to delta r, so this is going to be 0. So this is going to be 0. So this part remains same, this delta w by delta mgr. Okay. So if I demand that this work done is 0, so this is I have two components. This is one force, which is my applied force, this is mg, and this is the constant force. Okay, so this is Fia, and this is Fi. This is the constant force, say the constant force C. So what is there in principle of virtual works? That is Fia dot delta Ri is going to be 0. So if you remember this that this is my principle of virtual, the applied force dot delta Ri is going to be 0. So and this is by virtual work. So here in this case, this is 0, n dot dr is 0 because n is my constant force, and because it is perpendicular to virtual displacement, it is going to be 0. But this the work done by the virtual displacement for delta r by this applied force, which is my mg, if I demand that is going to be 0, so then what is then only then this my bead is going to be in a static equilibrium. If I suppose that this bead is in a static equilibrium, the two forces which are acting on the system, that is the n and mg, if because of that this bead is not moving in a static equilibrium, then I can find the condition for that by demanding that this is going to be 0. So this gives the condition for the equilibrium or static equilibrium, that the component of the mg, because mg is in direction, it is going to have two components. So this is mg is in direction, so one component is like this and one component along the displacement. Okay, so this component of mg component, this is like say component 1, so this is component 2, so this is my mg and this is my normal force. So this is balancing this component, but if this bead is going to move along this direction, so the movement could be because of this component of this component of my mg, the applied force. So if I apply the condition that system is in static equilibrium, so then what I demand that this the component of this mg, okay, along the wire is going to be 0. The component of the wire, the component of mg along the wire is 0, then only the bead is not moving, the bead is going to be in a static equilibrium. So you see that by applying the virtual principle of virtual work, we can actually find the condition for mechanical system, that under what condition it is going to be in static equilibrium. And we see that we discuss about this principle of virtual work and applied it, but we see that that is for static equilibrium, that the forces are acting and but there is no motion in the system, that is V is 0. But we want to be true only for the dynamic equilibrium, that if the forces are acting and then system is motion are there because of uh, with the uniform velocity, basically there is no acceleration. So we want the dynamic equilibrium for the system. So for that we have the principle which is known as the D'Alembert's principle. So we know that the principle of virtual work applies to system with a static condition. So but we want the condition to be for the dynamical equilibrium, and that is done through this Newton's second law, because Newton's second law tell us that this Fi, the force applied, is the rate of change of the momentum, that is Newton's second law is F is dp by dt. So I can write this rewriting as, if I take this Fi minus Pi equal to 0. So this is basically, if I say F plus of minus P dot is going to be 0. So whatever the force I am applying, there is a reverse effective force. This is my reverse effective force as an oppositely directing to this what I am applying the force. That's why the total effective force acting on the system is 0, and then the system is in dynamical equilibrium. Beside it is in motion, because like when the car is moving on the road, the force provided by the engine, that is to the tire of the system, and then because of the rotation of the tire, the force is applying on the road applied by the tire on the road is in opposite direction of the motion, and because of the friction being applied in the direction of the motion, those two are responsible, are being opposite to each other. But so if the car is moving with the uniform velocity, that is it is in dynamic equilibrium, those two forces are acting but there is no acceleration. Okay, so neither this force is which the car is applying through the tire to the road in the opposite direction, and the friction in the direction of the motion, that is balancing each other like this, and then this is going to be 0. So the car is moving with the uniform velocity, and there is no acceleration. That is the condition of the dynamic equilibrium. So this will reduce this principle will reduce the system from dynamic to static. So okay, so when we have a system like this, if I apply a force, and then you see it will produce a momentum, because F is dp by dt. This will produce a momentum of P. So if minus P is acting on the system, minus P dot is acting on the system from here, so then the system, this block is now in a static equilibrium. So principle of Virchow for a static equilibrium. Now we, through this, if I apply, my system is in dynamic equilibrium, then if I apply this D'Alembert principle to the system, then my system is going to reduce from dynamic equilibrium to a static equilibrium. So now the expression for the principle of Virchow work reduces to, because the principle of Virchow work says that this the work done to for this Virchow displacement through this applied force Fi is going to be 0. So my Fi here is my, if I apply the applied force and the reverse effective force, that is my in the opposite direction, Pi with delta I is there, and this applied force consists of, this total force consists of the applied force plus the constant force, and that is minus Pi with the Virchow displacement. If I separate it with this applied force and the constant force Fi minus Pi dot delta r equal to 0, because in case of Virchow displacement delta d equals to 0, the displacement of particles in the system which moves in accordance with the Newton's law, the work, there is no work, that is going to be 0. So that is Fi delta r, what we demand is going to be 0. So when this is 0, so considering only the non-deformable system, in which we have, when you apply the force, the system is not going to be deformed, but there is some imaginary concept is there. So this part which is left, Fia dot Pi, is going to be 0. So this is already 0 because of the work done by this constant forces are 0. So then the second part, which is A plus B, is 0, B is 0, the A is naturally going to be 0. This statement, that whatever the force I applied, and this is my reverse vective force acting on the system, and then these reverse vective forces are basically the inertial forces, and then so the whole statement is known as the D'Alembert principle. If you read out the statement here, that tells you the sum of the difference, that is sum of the difference between the applied forces. This is my applied forces Fi, between the applied forces and the time rate of change of the momentum, that is the inertial forces for all particles. What do you mean by the inertial forces? Here the inertial forces are all dissipative forces, which is, if I apply a force, then for example, if we have a frictional force which is opposing to this force in the negative direction and the system is not moving or in the dynamical equilibrium, that is my inertial forces, that is the time rate of change of momentum. These are MIA, velocity, and all these. So this is statement of the D'Alembert principle. And why it is important? Because it connects the Newton's law, because we have started from F is equal to dp by dt. So this is the Newton law, and if you connect Newton law to the principle of Virchow work, that from there I demand that this Virchow work is going to be 0 because of those forces which are reducing the dynamic equilibrium to the static equilibrium, and it helps to drive the Lagrange equation of motion. And we will see this part in the later lecture series. So how on the basis of D'Alembert principle we can derive the Lagrange equation of motion, and what is basically the Lagrangian of a system. So I hope this is clear to you. What is the principle of the Virchow displacement, that is for a static equilibrium, and the second was is D'Alembert's principle, which is for the dynamical equilibrium. Okay, this is all for today's lecture. We will meet again in the next lecture with different concept based on this D'Alembert principle, and we'll drive the Lagrange equation of motion. Thank you.